I don't have to start with 2 lectures on higher category theory. So let me do it like the other speakers and start with part 0, motivation. And if you're not happy with the motivation, you can then forget it. And or maybe not. Let's see. So we can. One of the advantages of stable infinity categories over triangulated categories that was already mentioned in one of the prepared lectures, Georg mentioned it, was that you can glue. We can glue infinity categories. What does gluing mean here? Let's just say we're taking limits or co-limits of diagrams of infinity categories, and this produces new infinity categories. And we would like to apply this in representation theory. And yeah, can we do this? This is kind of what we want to find out in this lecture series. And so this, of course, is a very broad question, so we have to narrow our focus a little bit. And we will consider a specific class. Consider a class of stable infinity categories. They are called topological Fukaya categories. Topological Fukaya categories. So if you're intimidated by the word Fukaya, we will not talk about anything Fukaya really. So it's symplectic, so don't worry about it. It will be topological. And they are equivalent to the derived categories of graded gentle algebras. And so why this specific class of examples? I mean, they're gentle, they're kind of easy, even though they're non-trivial. But nevertheless, I mean, they kind of, a lot of interesting things happen already in this theory with these sheaves. And yeah, we'll see this. So what specific will we do? So we will glue these, glue these categories, infinity categories, via constructible sheaves on graphs. Constructible sheaves on graphs and surfaces. So this will be the content of lecture 1. Lecture 1 is a general. So lecture 1 concerns the general context of what is the constructible sheaf on a graph and what is its global sections and what is this gluing context. And then lecture 2 is specialized to the gentle case. Specialize to gentle case. So lecture 1 is constructible sheaves. And then in lecture 3, so this morning we saw in Jan's talk the geometric model for gentle algebras, which describes part of the representation theory of these gentle algebras in terms of the surface. For instance, objects correspond to strings, which correspond to curves in the surface. And we'll kind of have a sheaf perspective in lecture 3 on this geometric model. Perspective on the geometric model. And then lecture 4 will be a surprise one. And before we get into this, I would like to kind of mention an organizational principle or kind of idea for how sheaves of categories work and what they do, which is called the macrocosm principle. Which was proposed, I think, in a paper of Ayala, Mesolji, and Rosenblum, called, what is it, stratified NC geometry. Stratified NC geometry. So, if you have a gluing context, so this will go in the next workout. If you have a gluing context this comes with the following features. Firstly, you have the macrocosm or macro gluing, which is you glue the categories. Categories. In our gentle situation, this will correspond to we glue topological Fukaya categories. Fukaya categories. Then you have the microcosm, or the microgluing. And somehow macrogluing implies microgluing. And what is microgluing? This means that you glue objects. And what will gluing objects correspond to in our setting? It will correspond to objects from curves. Why that? So, why is a curve a recipe for gluing? Well, a curve is composed from, in a surface, say you choose a triangulation of your surface, and we already had earlier that you can intersect your curve with this triangulation. You get segments of the curve. And this curve is obtained by composing these segments. And this is a recipe for gluing together local objects to a global object. And so microgluing, in the gentle case, is just curves give you objects. And then there's the nano gluing, which is you can glue homs. Let's say R homs. And this, in the gentle case, corresponds to describing homs in terms of intersections of curves. So you can take these gentle sheaves that we'll discuss. You can take them as like a class of examples where you can see this general principle of how gluing contexts work in play. And then let me also, before we start with the constructible sheaves, advertise a little bit this machine. So advertisement. What are other classes of examples appearing in representation theory and beyond, which can be treated by this formalism of sheaves of categories? So other classes of stable infinity categories that can be treated by the same methods. So this includes, we have gentle algebras. There are derived categories of skew gentle algebras or graded skew gentle algebras. As recently worked out by Barmeyer, Schwalb-Wang. Is Wang away? Let me check. Wang, thank you. And then you have also derived categories of possibly relative Ginsburg algebras of surfaces. Algebras of surfaces. Worked out with mine. Then you have derived categories of graded Brouwer graph algebras. So you may know Brouwer tree algebras from modular representation theory. They're a version of this, Brouwer, or generalization of these Brouwer graph algebras. This was worked out in joint work with Haydn and Xu. You have Fukaya-Simon categories. These all come from some sheaves on a surface. And then you have a much more general context in which sheaves of categories appear, also coming from the symplectic Fukaya literature, which is sectorial descent. Sectorial descent for partially wrapped Fukaya categories. Right. Fukaya categories. It's worked out by Ganatra and Schender. So in their work, they produce large classes of co-sheaves, of categories, which they maybe go a bit beyond what we're discussing in these lecture series, but nevertheless, some of the methods and definitely this principle of macrogluing, nanogluing should apply in that context as well. So there's plenty of examples, known and not yet known, and I will now start with the actual lecture one. Which is constructible sheaves. Sheaves on graphs. So throughout this lecture series, we will be working on surfaces and graphs embedded in surfaces, and we'll now start with this somehow very with this geometric context, defining this, making it precise. Somehow not very hard to say what it is. So a marked surface is a pair Sm with S is a what is it? It's a compact oriented topological surface. Oriented topological surface with non-empty boundary, and M is a subset of the boundary such that it's a finite subset, such that every boundary component, so this is the set of marked points. Every boundary component contains a marked point. This is for simplicity. You can relax this assumption, but it's already difficult enough. We will just do this context. So every boundary component contains a marked point. This is that mostly for convenience. And then, what is a graph? Graph G. It has a finite set of vertices and edges, and we allow so-called external edges. So, what's an external edge? Let me draw a picture. So, this would be a graph. It has one internal edge and four external edges. An external edge has the feature that it only has one vertex, which it is incident to. And then the other end is just there. And every edge is composed of two half edges. Those are 1, 2 half edges. Half edge is just half an edge. And for simplicity,
do the external edges have half edges?
Yeah, external edge is one half edge.
One half edge.
For simplicity, those half edges will only appear once or twice in the lecture series, so don't worry too much about them. For simplicity, we will forbid loops. I mean, you can do everything with loops, but just want to have everything somehow as easy as possible. So let's just not worry about this. And then this, what is a loop? This is a loop. So this would mean that an edge is incident to the same vertex twice. And once you have loops, you have to always say which incidence of an edge with the vertex you're referring to. This is annoying, so this is why we remove these. Okay. So if you have a graph, you can talk about its geometric realization. This is a geometric realization of the graph. Of G, which is the corresponding topological space. It's a simplicial complex if you want. Let's say this is the top. And so, definition, what is a spanning graph? So a spanning graph of a surface. Spanning graph of a G. So, or we call a graph G a spanning graph of the surface S if we have, so We'll kind of be a bit cheating here, so you have this embedding of the geometric realization inside of the surface, but I never want to specify it. I always have it implicitly. So if I say a graph is a spanning graph, I'm choosing an embedding of the graph in the surface, but I will never say that explicitly because it's impractical. So it's an embedding, satisfying two things. Also, it's an embedding in the complement of the marked points. Such that, so first of all, I is a homotopy equivalence. Homotopy equivalence. And secondly, I induces a bijection. Induces a bijection between the external edges of G and the connected components of the boundary of this surface. Connected components. Of the boundary of the surface without the marked points. Let me draw an example on the next board.
Is the I here part of the data of a spanning graph, or is it that it has the property that there is I?
Yes, so it's part of the data, but I'll never actually specify it.
Can you push up the board?
Oh, sure. Is this because of the reflection or because you can't read it over?
Because of the data.
Do I have to break this or not? Or can I just read it? Should I break this straw or not? Okay. Sometimes you have to break chalk so it doesn't.
In general, do you have like connected assumptions or does it matter?
Oh yeah, let's say all surfaces are connected and hence all spanning graphs are connected.
Okay.
Yeah. So example. So a good example of a surface is the annulus. And then let's put some marked points on it. So which color is the? Have we tried orange?
Should be fine.
Okay. Red is somehow surprisingly not the right one. You put one mark point here and one mark point here.
Is it, if you open the drawer, there's a big thing.
Oh, okay. This one?
You get to borrow it.
I might use it. Let's see. Okay. Okay. Yeah, very happy. So what's the spanning graph for the annulus with two marked points? It has to be homotopic to the circle, right? The annulus is homotopic to the circle. So let's start with two vertices and two edges. This is very homotopic to the circle. And then we want the external edges to exactly be, well, there's supposed to be one external edge for every boundary component, because there's one marked point for every boundary component. So let's say this is an external edge, and this is an external edge. And then this is somehow more or less the minimal choice. Well, I'm not exactly, I could contract these two. But then we can add some more redundant vertices, and this doesn't. Some things that we're not allowed to do. So if we say we do this, then this wouldn't be a spanning graph anymore, because then it's not, you're getting extra circles. So let's not add this edge. Another thing we're not allowed to do is say add another external edge, except if we add another marked point. So you see there's somehow a lot of spanning graphs for one surface. They are, you can always add more vertices to them, as long as you don't change the homotopy type. Yeah, question?
So you said that it's induced by actually the external edges in connected values? So
By intersection. Yeah. When every external edge to intersect one connected component of the complement of the marked points on boundary. So our surface was oriented, if you remember. So the orientation gives us a notion of clockwise. So orientation S induces the cyclic order, the counterclockwise, cyclic order on half edges of G at a vertex. So what is this in this example? I think this is counterclockwise, and you get such a cyclic order every vertex. If you have a one-banded vertex, well, it's you're putting a cyclic order on a set with one element that is a unique one. That's also true if you have two edges. Three vertices higher, you do get some, you get something in. And the graph equipped with such a cyclic order on the half edges is called a ribbon graph. G is a ribbon graph. So any spanning graph of the surface will inherit from the orientation of the surface a ribbon graph structure, as in this painting. Drawing. Okay. Any questions? Then let me now define the category for you. The exit path category. Exit of the graph, and I'll call it category, but it's actually an infinity category. Is the nerve of the one category with, so we learned yesterday, you saw that we have one category, we can get an infinity category by passing to the nerve, and we find one category, we just need to give objects or morphisms. So this is how we can find an infinity category here. So what are the objects? The objects are the vertices and the edges of G. And the morphisms, which are not the identity, of course you have the identity morphisms, but let me specify the other morphisms. They go from a vertex to an edge. This is a vertex. This is an edge. And E is incident to D. This somehow. Morphisms go from vertices to edges, unless they're the identity. And
this is a poset.
yes, it's even a poset.
Even like by part.
Exactly, yeah. This will be super important in 15 minutes if you wait. Only 30 minutes, no, 15. So, example. The other favorite example of a surface, and maybe the idea this isn't a favorite example, is the square, or generally an n-gon. Maybe the triangle is the one. And then, so this is a triangulation of the foreground. This has a dual graph. And so generally if you have a triangulation, you can get a dual graph by putting a vertex in every triangle, namely a triangular vertex. And then you get why it's dual. So this is the graph, and let's label its vertices and edges. E1, E2, E1, E2, E3, E4, E5. Then X plus G, you can draw it as follows. So you have the two vertices, E1 and E2. You have E1, E2, E2, E3, E4. Kind of as easy as it gets. Didn't break. So why do I define the exit path category of a graph? Well, I think we're now done with this part on surfaces, on marked surfaces and graphs. And I now want to briefly talk about a more general context about on stratified spaces and constructible sheaves. I think last year there was a master class in Copenhagen on this topic. Maybe some of you in the audience saw the talks and know what I'm talking about.
The definition, it doesn't really depend on the surface, it's just measured graph.
Well, yes, but every graph is a spanning graph of the surface.
So,
Well, yeah, more or less. So you have to be careful with the marked points. The way if you drop the assumption that every boundary component contains a marked point, then it's true. Otherwise,
You can still see some pointers to the master class outside. It still has some of these exit signs.
Excellent. Yeah, then I can skip this chapter. We continue with the next one. So, what are constructible sheaves on stratified spaces? Sheaves on stratified spaces. So, this exit thing is a general construction. General construction. Taking as input a stratified space. And you can read about this in higher algebra, for instance. Not the first place where it was defined, but it's nice to read there. So, what is a stratified space? Very roughly. So it's just a topological space X plus nested subspaces. Nested subspaces. So you have x0 inside of x1 inside of xn, which is x, and then you call the call xi without xi minus 1 the strata. And then, well, you typically now impose conditions on this, so class conditions. And I won't define you any, so there's different notions of stratified space. There's, for instance, conically stratified space. So conical stratification. You can also talk about complex stratifications. And then there are many other ones. Smooth conical, for instance. And typically, your strata are manifolds. Sometimes they're even complex manifolds. And typically, they somehow increase in dimension. But, right. And if you have this, let me explain how the geometric realization of a graph is a stratified space. So G is a graph. Then G0 inside, this is the vertices of G. Inside of G is a stratified space. Stratified space with strata. First of all, you have, well, G0, the vertices, and then you have the geometric realization with G without G0, which are the open edges. And so if I have such a stratified space, so X stratified, exit of X is simply a set. With, so you can say what all of its n simplices are. Let me just tell you about 0 and 1 simplices. So 0 simplices they are the points on X. One simplices, they are maps from the interval, so continuous maps to X, which, this is where the name comes from, the exit strata. So what does that mean? So if I have such a, this is a path in my X, and if my path can either stay inside of one stratum, then everything is fine. Or if it wants to leave the stratum, it has to go to a stratum of higher index. So this is meaning like you're exiting, you're leaving the strata to a bigger stratum, and here you can draw a picture and we'll see what it sees. So if, let's say your stratified space is 0, then the real positive real axis, and then positive half plane. And then you have, let's try this out. You have a path, which for instance, it could start here, actually works. It could go here, and then it could exit. This would be a perfectly fine exit path. And another example of an exit path is it would start here, and it would go here. I can also, I don't have to go to the next adjacent high dimensional stratum, I can just jump. In the case of a graph, of course, what are my exit paths? Starting at a vertex, well, they start at the vertex and then they go to the edge. This is, those are the exit paths in a graph. And this is why in the exit path category of a graph, the morphisms go from the vertices to the edges. One more comment about this. So this is a general exit of X is a general definition, which you can feed any stratified space in there. If your space is conically stratified, and I think that's all you need, then it's even an infinity category. But it's somehow not the same definition as the one I wrote on the other board. The definition is slightly different, but it's equivalent as an infinity category. So this is the point. That in the case of graphs, this exit path machinery is actually easier than in general, or you somehow. So the fact that every edge of G is contractible, this contractibility property means that somehow you don't have to worry about any homotopy stuff when doing this exit path thing. So there's a question.
Yes, but the exit I'm only allowed to exit once.
No, you can exit as many times as you want. But you can't enter again.
I'm allowed to go from A to B to C as long as ever.
Yeah, absolutely.
But what's the problem with not always? Why do you conically stratify that? Isn't it?
For it to be an infinity category?
Yeah, but can I just compose those? I thought the problem with conically stratified is that you only allow the ones where you exit once. Maybe we need to.
Yeah, maybe we should check high algebra before I say anything incorrect. Yeah.
Because it seems like those you can just compose. I don't see it.
Yeah, but I mean, you need more than just being able to compose, you also need higher things, but maybe you're...
As a category in terms of logical spaces, I don't think there's a problem.
Okay.
I don't know.
Yeah, you're making a good point. I don't know if someone knows the
answer.
answer. Yeah, I should have read the chapter before. Okay, well, this is somehow not so relevant for us. Exit of G is clearly always an infinity category, and yeah, we're mostly interested in the case of graphs. And so every edge of G is contractible. The definition of exit of G, or this means that exit of the stratified space G is equivalent to exit of G of the graph. So there's somehow up to homotopy. There's a unique exit path exiting the vertex and arriving at that edge.
The constant path is also allowed, which doesn't exit.
It's the identity.
Yeah.
The constant path is the identity. Exactly. And on the contractible space, every path is a homotopic to the constant path. All right. So, so what's a constructible sheaf? stratified space X. This is a sheaf F on X, such that F restricted to any stratum is locally constant. And then there's a theorem in this specific version due to Porter-Tessier, which says that let X be a conically stratified space. Conically stratified space, which is locally sufficiently nice. It needs to be locally constructible or something.
I don't know what conical means.
Yes, so graphs are conically stratified. And this just means that, so this is about certain neighborhoods of strata, which are basically cones. Let's not try to define it here, because it will be beside the point. And just take this as any stratified space you typically encounter, or you can imagine is conical. Like there's, sure there's conic examples, but like in practice, most examples are conical, and it's a mild technical assumption. Is that good enough?
Sure.
Okay. So locally sufficiently nice also. For more details, I refer you to their paper. And then C is an infinity category, and then some of the technicalities don't end here. You have to put completely generated. And we definitely didn't learn what that means in this today in the preliminary courses. Completely generated. So if you're not an expert on infinity category theory, feel free to ignore this. It will be fine for us. Then then constructible sheaves on X valued in C. Constructible sheaves valued in C. They're equivalent to functors from the X category to C. So we will be interested in constructible sheaves on graphs. And you don't need to know what a sheaf is, you just need to know what a functor is and know this definition. And this theorem tells you that you're working with a sheaf. This would be kind of the point of this lectures. That somehow there's a nice sheaf context, but in the context that we're working with, it's all very simple. Why does this theorem make sense? So if I have a sheaf here, let me erase there right now.
Can you relax compactation?
If you know something about the problems, so they proved down a theorem about hypersheaves, and then they use completely generated to deduce that hypersheaves are the same as sheaves. So if you know that hypersheaves are the same as sheaves, then you're good. They do need presentable. So for X, this graph coming from a graph. And F a constructible sheaf, then you take, let's say we take V, the vertex, an exit of G. The functor from exit of G to C, it will map V to the stalk of F at E, and then edge E will map to the stalk of F at any point on E. So you can draw this like this. Let's say we have our graph here. Then here you have the stalk V, here you have E. You choose any point, say P, to compute the stock, you're taking local sections. To compute the other stock, you take local sections here. And then local sections at V, you can restrict plus parallel transport. So transport gives you a map from f of V to f of A. So the sheaf, the restriction maps of the sheaf, they give you these maps between the stocks. And this is morally what this theorem means in this case. And from now on, call functors x of g to C constructible sheaves. And then we're specific in a specific C, namely we set C to be the compactly generated. So we're very lucky somehow that the category of stable, so the compactly generated infinity category of stable infinity categories, exact functors, and let me add a small here. No. It's a compactly generated infinity category of small stable infinity categories. So we're very lucky that stable is compactly generated, hence the theorem applies. Okay.
Can you name the compact category?
I can name a paper where it's true.
Can you respect this?
Yeah?
Well, finally.
That makes sense.
It's slightly non-trivial, but
Yeah, all of these are technicalities, which, I mean, if you're doing representation theory, none of this really matters. But it's kind of, it's in the background. So. So now, if I have a sheaf, what am I supposed to do with the sheaf? I'm supposed to take global sections. So now we have to translate. I mean, if you have a sheaf, an honest sheaf, in the sense of sheaf theory, you can take global sections. What does that mean if you reformulate your sheaf using exit paths? It's actually really easy. You get the following definition. So f exit of G is stable, constructible sheaf. The infinity category of global sections of F is, so you will denote this by R gamma GF. And this is simply the limit of F in stable. You have, F is a functor, right? I can take its limit, and this limit is the global section. So, and now maybe you remember to this morning's lecture by Matteo. So, first one comment. So, recall the forgetful functor from stable to cat infinity. This preserves limits. So to compute global sections of constructible sheaves, well, you can say infinity categories, you just have to compute limits of infinity categories. But even better, they're all somehow strictly commuting diagrams. Remark, every functor f from exit of G to stable, or let's say cat infinity factors through, or factors as, so you go from exit of G to the nerf of set delta, simplicious sets, and then you take the localization. Localize cat infinity. And this is f, and we will call this small f. So what does this mean? We discussed this morning. So if you have a diagram in an infinity category, this diagram does not strictly commute. You can't. There's always these two cells and higher cells, which kind of make life much coherent. And here we're in the fortunate situation that our exit of G, it has objects and morphisms, but it has no n simplices, which are so exit of G has no non-determinate, has no non-degenerate n cells, n simplices. This is for n bigger or equal than 2. And because all of the higher cells, simplices, are degenerate, so this comes from the fact that it's a poset with which is even binary, as Gustavo mentioned earlier. And this fact just means that if you have a diagram indexed by exit of G, it always factors through a diagram, a strict diagram of simplicious sets, which not every diagram in cat infinity comes from a strict diagram of simplicious sets, or is equal to a strict diagram of simplicious sets. But here, will always be the case, and so this will be kind of relevant. So this means that f strictly commutes, or is a strict diagram. Is strictly commutative.
There's nothing to check.
Yeah, there's really nothing. But this is somehow very important, because if you were working with sheaves of categories in a general constructible sheaves in general stratified space, this wouldn't be true. And so somehow on graphs and surfaces, this just makes the theory so much less technically complicated, because everything is strict. And why specifically? This we also saw in the materials lecture. So there's a theorem, which, let me give you the Caradon tag. It was also in Matthias' talk. It's Caradon 03AB. So if you take f from exit of G, f nerf of set delta, going to cat infinity. By the way, this notation, small f and capital F, we will keep it throughout the lecture course. So, let me. It looks fat, but actually it writes small. Always use this notation. So this is kind of. Later on, I will always write small f for this factorization, which there is, and I will not say this again. So just have this. So let's have such a diagram. Then limit of f is equivalent to the infinity category of coCartesian sections. Cartesian sections of the Grothendieck construction. Grothendieck construction, we denote it by P from gamma of f to exit of G. So somehow maybe the main goal for me of this lecture series is to explain to you that this theorem is actually meaningful and easy. Or, well, not proving it, but like the statement in the case of graphs is somehow very concrete, a very concrete thing. And stay tuned to learn more. First, though, another definition. So again, f exit of G, let's go to stable, constructible sheaf. The infinity category of lax sections is denoted by L, GF. So this is, let me first write it in sloppy terms and then in precise terms. This is all sections of P. And precisely, this is the following fiber product. So you take functors from exit of G to stable, and then you compose with P. This gives you a map to functors from exit of G to exit of G. And then you want this map to be the identity. And so you are saying that this is a section of P. I just wanted to say what a section is once, so that it's clear. A section is a map from, sorry, not stable, gamma of F. It's a map from exit of G to gamma of F, such that when you compose it with P, you get the identity from exit of G to exit of G. So this is what a section is, and we can take all sections, and we get a new category, which I call Lex sections. And if you take so-called coCartesian sections, you get the global sections. You can now ask, what are Lex sections? How should I think about this in terms of classical sheaf theory? And the answer is you cannot. No, I think I should erase over there.
In terms of like descent, like you just have sheaf of one categories. Is there an analog of this that's clear?
Not even, so we will talking about this more. I was kind of teasing you. I'll now tell you something about this. So first of all, first comment. We have a fully faithful functor. Descent. Yeah, in some sense yes, but yeah, we will see. Fully faithful functor from global sections into this grid-like section. And this is just because the category of coCartesian sections is by definition the full subcategory of all sections which are coCartesian. So this fully faithful functor is by definition. And then, so just to give you a bit more context, you don't actually need to understand this, is that this is the infinity 2 categorical Lex limit of and because there's a 2 here, this has no analog in classical sheaf theory. Analog. And however, this will actually be super helpful, this category, to construct, or if we're only interested, we will only be interested in this guy, which is our topological Fukaya category, or derived category of a delta algebra, and we will need to use this fancy guy to study this guy. But yeah, that will be lecture 3. So for now, let me try to make concrete what all the things I wrote. So let's choose a specific graph.
Well, sometimes why you're using things a bit more basic than you want to use.
Yeah, I'm using a different chalk.
Oh, okay. So this
Can you still read it? And let me use the other chalk.
Yeah.
It breaks so often. It's someone like me, it's not ideal. I'll use a broken piece.
What's the harder more?
I have to press harder.
Okay. Yeah.
Or whatever. Let's see. So exit. What is exit of G? Well, it's just E goes to E, which is delta 1 if you want. If you like some special language. If you don't like some special language yet, you will at the end of this course. So the functor F from exit of G, which is stable. It's the same thing as just a factor A, F, B, where this is F of B, and this is F of B and F of B, right? Let me continue writing directly below it. So what's a coCartesian section? Cartesian section. Those are sections. So I'm now looking for a section of this, well, not of this diagram, but of the Grothendieck construction over delta 1. So here we go. So gamma of f goes to delta 1, which is exit, which goes to E, and then the fiber, if you form the fiber over B, you get A, and the fiber over B over E, you get B. This is how we define the Grothendieck construction this morning. It's a category, its objects are pairs. You have an element in the base and an element in the image of f at that value. So if I say B, then I have an element in B plus an object, B plus an object in the value of f at B, which is A. So this is a category, and one object, we maybe write it like this, let's say objects. Gamma of f is the objects of A, disjoint union objects of B. And they are the two fibers over delta 1. So you think of this category as a union of the two categories, with morphisms going from A to B. And then section. Right, what's a section of gamma of f? Well, let's first do sections. So first I have, so this is the same as a map like this, which gives me the identity. This will be a section, right? So section maps 0 to A and 1 to B. So what is it? A section. This is map from delta f, gamma f, delta 1 identity. The same thing as, first of all, an object xa in A, and then an object xb in B, where this is a subcategory of gamma of f, and then you have a morphism here. And what's a morphism from xa to xb in the Grothendieck construction? It's the same thing as eta morphism, or a morphism from f of xa to xb in B. So by definition, a morphism in the Grothendieck construction from an object in the fiber at 0 to the fiber at 1 is a morphism from the image under the functor of the first object to the second object in the fiber at 1. This is the definition of the Grothendieck construction. And what is it? What is a coCartesian section? coCartesian section. This would be a section of the form xa shriek f of xa, where a shriek here means that the corresponding morphism here is the identity or the equivalence. F from xa, identity f. And clearly these guys are, well, this is a subcategory of those guys. And then there's another way to compute the limit of f, right? G is, exit of G is the one simplex. If you have a diagram indexed by the one simplex into computing the limit, while the one simplex has an initial object, thus the limit is just the value at the initial object. This is a general thing in category theory you may have seen in your life. So the limit of f is equivalent to f of b, which is a, since b inside of exit of G is initial. So how is this category of coCartesian sections equivalent to A? So this functor from A, from A to the global sections R gamma GF. This will map an object A to XA to the coCartesian section XA should have an XA. Okay. So we haven't really seen many local sections. So next time probably we'll discuss card extension and how you can produce lax sections out of local sections. But that's for another time. So yeah, thanks for listening.
Any questions or comments from you?
Just a question. Could you say one again, the coCartesian section? Like, don't
Right.
explain it.
Yeah, right. Let me give a proper definition because this is important. This is some. So if you have this guy. So recall if you have gamma of f over exit of g, and let's say we have delta 1, which maps 0, 1, maps it to v goes to an edge. And then if you have a map like this, it's a partial section if you want. What is such a thing? It's the same thing as somehow you have x0 in f of v, you have x1 in f of v, plus a map from v to e of x0 to x1. This is a section here, and this is by definition of the Grothendieck construction. What morphisms look like in this Grothendieck construction? They are by definition such a thing. And then definition, call delta 1 to gamma of f. So this is the same thing as an edge in this infinity category, as a morphism in the infinity category. A coCartesian edge, if, let's call this guy the eta. Eta is an equivalency. So this means that this section is thus determined by its value at 0. The value at 1 you just get by applying the functors. And then, I mean, this is not a strict identity, but it's always equivalent to a strict identity. That's kind of the point. It's uniquely, sufficiently unique. It's up to contractible choice, it's equivalent to the identity. If we made the right statement. And thus, and then this is a coCartesian edge, and then a coCartesian section is a map from exit of g to gamma of f to exit of g is the identity such that for all edges v to e in x of g, let's call this x of v to e is coCartesian edge. So a coCartesian section just means that all the edges in the image of the coCartesian section are coCartesian edges. And
Yeah, so it's like the value is determined by the initial thing, and the other one is just like the image.
Think of this as a sheaf condition. You have the stalk at the vertex, and then you restrict it to the stalk at the edge, and like the value of your section at the edge is obtained by restricting the section from the vertex to the edge. Of course, there are hidden equivalences in there. If I have an edge that comes from two vertices, these two sections at the two vertices will both restrict to the edge, and then they will be equivalent at the edge. There's somehow like some equivalences hidden there. But this is it's like basically this is why this corresponds to a sheaf and not a lax section, the actual section of the sheaf. Other questions?
Okay, let's
Let's thank Merlin again.